All right, this is a pre-video for section 5.1. We will have a worksheet that goes along with these notes, a daily worksheet on our first class of next week. So let's look at what does it mean to be an inverse function. This is actually a very easy topic to talk about, but we need to understand what it actually is because it helps us understand what the rest of chapter 5 is about, which is two very special functions that are inverses of each other, exponentials and logs. So a function may have the same value for different numbers in its domain. For example, if you have x squared as your function, 2 and negative 2 both square and equal 4, but negative 2 and 2 are different x values. So before, remember when we defined what a function was, we said each x could only be used once. We didn't care if the y of 4 had popped out twice. That's just when you want it to be a function. For a function to be what we call one-to-one, each x can only be used once and each y has to be tied to a specific singular x. So in other words, you can't have the case where negative 2 and 2 both get squared and equal 4. So for a function to have an inverse, it has to be one-to-one. In other words, each x and y are both unique. So each x can only be used once and each y can only be used once. What this means graphically is that you have to pass something called a horizontal line test. Notice that this graph right here in this picture definitely passes the vertical line test. The blue graph, if you draw vertical lines, each vertical line will only touch my graph once per vertical line. But this horizontal line here, the HLT, our graph touches it twice. What that means is that this y value was the same, but the x values were different. That means your graph is no longer a one-to-one function, which means it also doesn't have an inverse. So to figure out if a graph is going to have, or any function is going to have an inverse, if you have the picture in front of you, you can just do the horizontal line test. Before doing the horizontal line test, though, you do need to make sure you're even looking at a function. So we really say do the vertical line test first to make sure it's a function, then check the horizontal line test to see if it's one-to-one. So let's look at some examples. This first one here is definitely a function. It passes the vertical line test. It also passes the horizontal line test. Each horizontal line crosses this line only once. So this one would be a one-to-one function. This one passes the vertical line test. Imagine drawing vertical lines all the way through. So this is part B. Each line would only cross the parabola once, but it fails the horizontal line test. So this is not one-to-one, just a function. So that means this graph would not have an inverse unless we learn something else in a little bit, which is called restricting the domain. If we only used half of the parabola instead of the whole thing, we would force it to pass the horizontal line test. So it is possible, even if a function is not one-to-one on its entire domain, we can restrict it to part of its domain. For this one, it passes the vertical line test, and it also passes the horizontal line test. So this one would be one-to-one. This one does not even pass the vertical line test. So obviously we don't even care about the horizontal line test because this is not even a function. This one passes the vertical line test but fails the horizontal. So not one-to-one, just a function. This one fails the vertical line test, so not a function at all. This one passes the vertical line test but definitely fails the horizontal line test on multiple accounts. So this is not one-to-one, just a function. And this one fails the vertical line test, actually. You have two closed endpoints in the same vertical line. So this one's not even a function. If that had been open on one of these, we would have been okay for the function part, but it would fail the horizontal line test because all of these little sections have multiple points on the same horizontal line. So if you have a graph in front of you, to figure out if something's going to have an inverse, you just have to do the vertical line test to make sure it is a function, and then the horizontal line test to make sure it's one-to-one. Now, if you don't have the graph in front of you, there is another way to prove something is one-to-one. What we do if we have an equation, so from an equation, we use a scale we picked up in section 3.3 or 3.4 of the last unit. We're going to set f of a equal to f of b. We're going to do two different evaluations of the same function where we let x be a one time and b a different time. And we want to try to prove that a actually is the same as b. So if they have the same y value, it has to be the same x. So for example, if I do this one, I would say f of a equals f of b. And normally, just so you don't get too stressed out, we don't put this on the test. But it is the only other way you can tell if something is a one-to-one if you don't have the picture in front of you. So that's 1 over a minus 2 and 1 over b minus 2. We can cross multiply here, and then we can add 2 to both sides. And notice that gives me b equals a. So this one is one-to-one. What we've just proved is that if you plug in different x's and they give you the same y, the only way it can be one-to-one is if the x's were actually the same x. This is one that's going to fail. So I wanted to show you one of each. We don't spend a lot of time on this because, like I said, this is more of an upper level skill. But we wanted to show you that you don't always just have to have the graph. I already know this is going to fail because it's a parabola, and parabolas don't pass the horizontal line test. So a squared plus 4 equals b squared plus 4. When we go to subtract the 4's, you get a squared equals b squared. But when you physically draw in square roots to get rid of the square, you have to write plus or minus. So what we don't know is we don't know if this is a positive on one side and a negative on the other, or both positive or both negative. This is not clear. It's not clear that regular old a equals regular old b because we don't know what signs could have been on either side. So this one is not one-to-one. So that's how you would do that algebraically. So why do we care? So what's the whole point of this? So if a function is one-to-one, what we can then find out is that when you have a function, you have a bunch of operations, like x plus 3 over 2x minus 5. And that is a set of directions that tells you how to plug in an x and then find a y. What the inverse function does is you start in the other part. You start with that pretty much the range of the original equation, and you learn how to map back to the old domain. So the cool thing is that what's happening with an inverse is that the range of the first function is the domain of the inverse. You're learning how to go from an input to an output and then start at that output and go back to the original input. You're learning how to map back the other way. So the cool thing about this is that if x goes to y, we're going to learn how to take that y value, and it's going to be our new domain, and we're going to plug it back in and find a new x, which is going to be the same x we started with. So these guys are just mapping. This one's mapping from x to y. This one's mapping from y to x. So you're learning how to go backwards. So what does that actually mean? Well, what that means is that the domain of the original is the range of the inverse, and the range of the original is the domain of the inverse. So those domain and ranges get flipped. So that's what's happening there. And then we do have a side theorem here that says you can prove two things are inverses without graphing them or without doing anything but a composition. If you do composition, g of f and f of g, and they both come out, because we're not going to change our letters, so they'll both come out to x, then you know that that means those two functions are inverses of each other. The reason for that is when you have two things that are inverses, so I'm going to have to scroll down for a second, I want to show you what they do on a graph. Okay, so anytime you graph two inverses on the same picture, they reflect over a very specific line. It's the line y equals x. So 0 is the origin, is our y-intercept, and the slope is 1 over 1. Notice that this is really interesting. You get these kind of reflections here. So this is an inverse and it's original. So original was kind of like half of a parabola. The inverse is a square root of x. So notice that here's something that pops up. This is the point 1, 2. On the other graph, that mirror image point is 2, 1. X and Y just get swapped. So that is essentially what happens in an inverse. The x's and the y's get swapped. This is the point 0, -3, or sorry, -3, 0. This one down here is the point 0, -3. Again, the mirror image has just been flipped. So anytime you have two inverse functions and you graph them on the same picture, they reflect over the line y equals x. So that's what we know about that. Okay, so just to lead us in, because I'm not going to do all the examples on the pre-video, but we're going to do at least one of a couple different types. This says use the theorem on inverse functions to prove that f and g are inverses of each other and then sketch them. So we're going to prove it two ways. To use the theorem, what you have to do here is you have to prove that f of g of x equals x. That's what we're trying to do. And g of f of x equals x. If you can prove this, then you can say they are inverse functions of each other. If you can't prove that for both of them, then they're not inverses of each other. So this is our goal. Okay, that's how you prove that they are inverses. So I do f of g of x. F is blank squared plus 5, and g is negative square root of x minus 5. If I square this, you square the negative and it will become positive, and the square root would just be x minus 5. Bring down the plus 5 and notice that the 5's cancel out. So yes, this one does equal x. The only way we can prove for sure that these are inverses, though, is to show that it works the other way as well. So negative and then square root blank minus 5. This is x squared plus 5 in here. So this is negative, and this would be, the 5's are going to cancel, that would just be square root of x squared, and that comes out to negative x. Now you think that's not x, that's a negative x. But here's something to note. In this function right here, the one that got plugged inside, which is one that where we started from, we plugged f into g. X's are always less than 0 here. That means this is a negative x. And a negative x is actually a positive x. So you had to know that about this domain that they gave us here. If x is less than or equal to 0, then that means the x that we see here is already negative. So a negative is a positive. So they both equal just regular old x. Now if we plot these, I'm actually going to use transformations of functions because these are parent functions. X squared, remember, is a parabola shape. But because we're only using x is less than or equal to 0, we're only getting half of the parabola. So remember, this is a transformation of up 5, and they said stay on the negative side of x. So this is this side of this parabola. And this guy right here is been moved right 5, and then it's reflected over the x-axis. Now you could just do these by a table of values. I'll show you that as well. But this is the shape like this. Remember, that's the generic parent shape. So normally it would be here at 0, 0, but we're going to move it right 5, and then we reflect it down. So the shape is like this. So notice if you were to imagine that line y equals x there, which I'm not drawing very good, notice those are mirror images of each other. If I didn't like graphing this just from transformations, I could have just as easily done a table. Just remember, when you do a table, you have to follow the rules for the domain. So I would pick 0, -1, and maybe -2. And for the other one, x's have to be greater than or equal to 5. So I would plug things like 5, 6, and 7 into this function. So notice that I could do this with tables, or I could do it with transformations for the graph part. So I'm not going to go through the whole table, but it could be plotted either way. All right, and then the last thing I want to show you today on the pre-video, because that'll lead us into a good place to start on our next class session, is how do you find the inverse of a function if you already know it's one-to-one. So they tell you to find the inverse, which means they're telling you it's already one-to-one. The key to this is the realization that in an inverse function and an original function, their relationship to each other is that their domain and ranges have been switched. So the first step to finding an inverse is to swap x and y. The second step is then to resolve for y. So what I mean by that, so we're going to just do two really easy ones. Y equals 7 minus 2x. I usually write the word swap, so I know I haven't done it yet and I need to. So that would be x equals 7 minus 2y. To resolve this, we need to get y by itself. So we'll subtract over the 7 and then divide everything by negative 2. So this would be y equals negative 1/2, because that's a 1 on top with that x. And that's negative 7 over negative 2, so that'd be positive 7/2. Now, the last thing we usually do is we write that as f inverse instead of y, because this little negative 1, like right there, that means the inverse. So anytime you see that symbol, you're talking about the inverse. So this would be negative 1/2 x plus 7/2. Now, in this case, the domain and range says find the domain and range of both. The way this will look on your test is we'll give you a little chart to fill in with spots for D and R, domain and range. This original was a linear equation, so remember that means the domain is all real numbers. So negative infinity to infinity. And a line also has a range of all real numbers. If you didn't know that right away, I'll show you how you could have figured it out. If you just find the domain of both of these, then the range and the domain, remember, just get swapped. So it's just across here will match and across here will match. This is also a linear equation. So because it also has a domain of all real numbers, that's why this one's range is all real numbers. So all you have to do is find the domain of both of them and then flip-flop it for the range. Now I'll show you one that actually has something, because there was nothing going on here. Everything was linear, so everything was all real numbers. If we look at B together, and this will be the last one we do on the pre-video because I want to do a couple of these in class together too. For this one, we write y equals 1 over x plus 3. And then remember, to find the inverse, we swap our x's and our y's. We want to resolve for y, which means we're going to have to cross multiply. So this would be x times y plus 3 equals 1. Go ahead and distribute that. Subtract over the 3x to get y by itself. So 1 minus 3x. And then divide by x. So my inverse function for this original of 1 over x plus 3 is 1 minus 3x over x. So there's my inverse. To find the domain and range of the original and the inverse, just find the domain of both. And you don't have to write these in interval notation. We usually don't specify that it has to be that way. So I'm just going to show you by saying x can't equal something since these are fractions. So for this first one, if you look back at the original, x could not equal negative 3 because that's going to cause a 0 in the denominator. For the ending, or the inverse, x cannot equal 0. So the original had a bad point at negative 3. The inverse has a bad value at 0. The only thing you have to do to get your range is flip-flop these. So 0 is the problem up here and negative 3 is the problem down there. But you do not want to write the letter x because range is not an x, range is a y. So that would be my domains and ranges. And that's it for our pre-video.